Alright, so today we're going to continue what we've been doing from our previous video, which we were able to compile the no operation language from our function. What I ended up doing last time was that I enabled TS check because there were some imports that I forgot to use. It's been so long since I've used vanilla JavaScript that it's just I need my typings. And we're going to continue the test passed. Now we're going to come with the next part of the book, which in here it explains kind of like the bytecode of what's actually going on. Remember that WebAssembly has different sections in which we start with, and I love this because it is very clear now with the magic version, which is there's 4 numbers in here, which we defined earlier on, and then comes the what was it? The version, the the definition of the type section, the function section, and the code section. Remember that each of these sections are already labeled, so they need to follow a certain order, and that's so the compiler understands and is much more efficient at parsing. The more predictable we have, the less things that we need to take into consideration. Now it says loose ends. Before we wrap up this chapter, we need to tie up a few loose ends. Integer encoding. A complete implementation of integer encoding is found in the deep dive on variable length integer encoding. Okay, and this apparently is going to be a part of the book, which is a deep dive chapter. That means it's strictly optional, and the optional genre in the book don't depend on it. Dun, 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 dun. Okay, at the end of chapter 1, we gave okay. We're gonna come back in here. I want to check this out. But right now, I'm just gonna get it out of here. Let's see if I can remove it from. Okay, I can do that. This is amazing. Like the other deep dive chapters is you're free to complete it at any time, but any of the helper functions written in this chapter depend on U32. So before we go, let's replace the naive implementation with a proper one. So the LEB128 was the algorithm, was it, for generating the, we talk about it, the encoding. The little Indian base 128 can encode up to 128 227 unique values per byte. So for assigning integers, it can go from 0 to 127, and for assigning integers, it can go to minus 64 to 63. So here it's actually showing the this part. If more are push, let me see, little endian bytes. Worry about the detail for now. Okay, with those cleanups out of the way. Okay. All right. Let me see if this actually covers it up. I'm gonna reload. Yes, your number was a WebAssembly numbers. Dun dun dun. Small and sign interior to LEB. Yeah. Here I think it actually breaks it down. I really don't know how to work with binary and with masks. It's really, we enter into binary notation when it comes to using only a single ampersand. Testing our implementations. Okay. All right. Okay, let's go. We're gonna dive deep today. Variable length integer encoding. This is a deep dive chapter that's been strictly optional. We're gonna cover it. At the end of chapter 1, we gave you the code for U32 and I32 and told you not to worry about the details. Now it's time to dig into those details. Give me a second. Okay, all right. In this chapter, we'll take a close look at how integers are encoded in WebAssembly. You'll learn the finer details of the LEB128 encoding scheme and implement a function to encode 64-bit integers too. The basics. LEB128 is a scheme for encoding arbitrarily sized integer. Use only as many bytes as required. It helps save space because small numbers, which are common in WebAssembly, can be stored in a single byte. And it says LEB128 is described as a dwarf debug information format document. I don't know what is dwarf. Okay, let's look for what is dwarf. I have no idea what is dwarf. No. I'm sorry, guys. I have no idea. Is a widely used standardized debugging data format. Was originally designed a long, executable, unlinkable format, although it is independent of object file formats. Interesting. Okay. I still have no idea what does that mean, but purpose and scope. This is very long. Holy shit, 325 pages. Dun, 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 dun. The Dwarf Debugging Information Format Committee was originally organized in 1988 as the Programming Language Special Interest Group of Unix International. Dun, 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 dun. Jesus Christ. It's a lot of information. This algorithm has two versions, one for signed integers and one for unsigned integers. Since the unsigned integers is simpler, we'll start with that one. So it says JavaScript numbers versus WebAssembly numbers. One thing that differentiates JavaScript from other languages is that JavaScript has one number type that represents both integers and floating point numbers, aptly called number. One of the things that we never tend to realize when we begin learning JavaScript, and JavaScript was my second programming language that I ever learned. The first one was PHP, was that we have different number types for that. You got the float based, you got integer based, you got unsigned integers, you got everything. And JavaScript just makes it like way simpler because it just have everything bundled together. And I think that's a really great advantage, especially when you are starting out, because you don't have to worry about that. You just think everything as a number. And that's amazing. But once you begin to learn other things, you understand that numbers are not all created equal. And there's a very big difference between float types and decimal types. And that can come and bite you, especially when you're performing arithmetic operations. Its underlying representation is a 64-bit IEEE 754 float. I think this is one of the traditional, right? Floating originally, yeah. Okay. Let's find out the limits by writing some code. Number that max safe integer. I didn't know that you can actually do this. Let us see. Come in here. Number max safe integer. Oh no, we oh wow. How many bits are there in the largest safe integer? I didn't know you can transform it to bits. String 53. The largest safe integer representable with JavaScript number is a 53-bit integer. What do we mean by safe? Let's see. Number that max safe integer. Oh, got it. It overflows, right? Or it starts together. Interesting. But we have a single largest integer type is I64, a 64-bit signed integer. Luckily for us, JavaScript added a new type called big int, which can represent integer of any size. We can so use to support WebAssembly's I64. To use big ints, we just need to add the n suffix to any integer literal. I don't remember this because big int is something that I don't use very often. We can go even larger than 64 bits if we want. Oh, interesting. I didn't know this. A small unsigned integer to lib128. Let's start with the algorithms for numbers, up to 53 bits, and later introduce changes to make it work with big ints. Here's a basic version that only works for numbers that fit in a byte. 7-bit, this code could be simpler, but this way it minimizes the difference over the next steps. Cause 7-bit masks. Bit masking. Let's go. Okay. 7-bit mask. So I'm gonna ask ChatGPT to explain me how this code works, because the thing is that I don't know a lot about bit masking. Explain to me what this code does. It's written in JavaScript. Let me see what it actually says. Here's what the code is doing step by step and what it means in practice. This is a binary constant equals to 127 in decimal. It's used to extract the lowest 7 bits of a value. And val, this extracts the lowest 7 bits of val. Can you explain to me what are the lowest 7 bits of val and why would you want to do that? And how the bit masking works? Below is the clearest, most concrete explanation of what lowest 7 bits means and why it is used in formats like lib128 and WebAssembly. Every number in a computer is stored in binary. A sequence of 5 zeros and 1. We know that. And it seems like the lowest 7 bits you count from the rightmost bits. The first 7 bits are the least significant bits, the ones that represent the smallest powers of 2. Okay, so 1, 2, 3, 4, 4, and 7. The ones that represent the smallest powers of 2. Okay, that I understand. That means that if we have a number in here, right? It actually says that it goes all the way to 1 and 28. So it says like, okay, we're gonna have the 3, 4, 5, 6, and 7, and we're gonna go this 0, this column over here. We are representing the 0, right? But if we add a 1 in here, that means it goes to number 1. Now, if we add a 1 in here, now if we go for the next combination, which would be 1 in here, 0 in here, and by the way, all of this are 0, 0, 0, 0, 0, 0. And 1 in here, this 1 becomes 2. So this means that it will have like up to 128 characters, right? And since we have like a 0-based index, it will start at 0, yeah. So to 127. What's 101 the lowest tendency? This is using variable length and integer encoders. Use it as they always using 4 bytes or 32 bits, because remember 1 byte equals to 8 bits. Encode small integer 1 by large integers in 2 or 3 more bytes. Each byte carries 7 bits of real data. The 8th bit, highest bit, is a continuation flag. Oh. 7 bits of the number payload and more bytes to follow. Small numbers encoded in 1 byte, large numbers encoded in multiple bytes but still compact. 7 bits at a time, because we can only store 7 real bits in each byte of LVB. But I think 127 was a prime number, wasn't it? So we should mask in 300, mask, full up. Top bit gets removed, masked out, the remaining bits. Okay, so we're gonna continue. So what's basically saying in here is that we're extracting the 7 meaningful bits in here because we're going to store this 8th bit as a part. So I'm gonna think that we're gonna use some sort of reminder of modulus function or something that we get the reminder. Because that way, the remainder, I think that's the right way to say the remainder. And that remainder, we're gonna get it we're gonna get that remainder and add it to the next flag somehow, right? And I'm gonna suppose this is gonna be 3, 4, 5, 6, 7. Yeah. And I'm just gonna fire off VS Code. I'm gonna move this thing to the right. I'm gonna close the console window. I'm gonna go back to utils.js. I'm gonna write here, say leb encoding. I say const 7-bit mask. I'm gonna say it's in binary format, right? And I'm gonna say 0 repeat in vim. Repeat and times vim. No, repeat and characters time vim. I know there's a way. I trigger it without me knowing. Okay, so I suppose this is gonna be okay. Control O 11. Oh no, right? I have this. I'm screwed. Well, 3, 4, 5, 6, 7. Got the 7-bit mask. Now we're gonna continue in here. I'm gonna say function leb128 v. Let val equals v. Const r. I don't know why we would define val like that. Val ampersand 7-bit mask. r.push b. And I think that we're going to be, besides using the modules, we are also going to use like a for loop, so we can extract all those things. So assign the argument v2val with a let, since we are going to modify its value. Initialize an empty array r to hold the resulting bytes. Use a binary and operator to get the lowest 7 bits of val and store them in b. Something that I have not done is to git checkout. Git init. Feature chapter 1. Entire chapter 1. Okay. I'll continue this. And now I am going to come back. Use a binary and operator to get the lowest bits. So very little knowledge. The widthwise and operator returns a number or big int whose binary representation has a 1 in each bit position for which the corresponding bits of both operands are 1. Yeah, I remember this. So basically when you put them all together, the one that matches the 1, it's the one that's actually gonna get it. This is very good for enums, for going like very low level, and for feature flags and everything. But this is a really bad way to do this, like day to day. Okay. Okay, there we go. Why 7 bits? Because the 8th bit of each byte will be used as the continuation bit. If it's set to 1, it indicates that the encoded number has at least 1 extra byte. If it's 0, it means this is the last byte. Since the 8th bit is going to be used as a continuation marker, it can't be used to encode the original number 8th bit. This means that any number whose 8th bit is set 128 or higher will require 2 bytes to encode. We can use the toString method, which is its optional radix argument, to see the binary representation of a number. All right. So 128, it says 10000000, which means if we're not going to count this, but we can safely assume that it's going to be the entire 0, like there are 7 zeros, right? And this would be right, the 1, which means that if we subtract them with 7 or divide by 7 and then use the remainder, can actually get it. Okay, so let's try encoding some number that should fit in a single byte to make sure it works. And this is running the functions. 0. To implement LEB properly, we need to process the input 7 bits at a time. We can do this. I want to see something. So in here, if I say, I'm going to copy this function. I'm going to paste it in the console. Make the console bigger. Okay. And I place LEB 129. It should return me 1. Oh, wait. LEB 128. And I put 129. It should turn me 1. Oh, my bad. I should probably have done this. Clear. Clear. And now I say LB 128, and then I say 129. So every time we want. This is awesome. It's really cool. To implement LB 128, we need to process the input 7 bits at a time. We can do that with the right shift operator. On each step, we'll shift the input 7 bits to the right, discarding the bits that we already encoded. We do that until all the remaining bits are 0. For every encoded byte, while the last one we set the continuation bit to using 1. Okay, one more. There you go. And we got a while loop. This was coming. This was really coming. So I'm gonna ask it. Okay, we're gonna ask now ChatGPT. So I really want to come here. Now explain to me this code. Seven-bit mask. The continuation flag. Oh, there you go. Okay. Example, data continuation bit, or. Encoded byte means another byte follows. Good. Now the function LEB128. File holds the remaining value to encode. Okay. More tells it we need another byte. R will collect encoded bytes. The main loop. Okay, I understand. And 7-bit masks. Shift away. This removes the 7 bits we just encoded. Oh. Alright. Alright. Got it. Original. So after and mask, you're going to remove this. Can you explain to me how the shift away works? Okay, move all bits 7 positions to the right, discarding the lowest 7 bits. Shift 7, the right shift. Okay, this is the visual example that I wanted. So there's a decimal number. Like, I don't know why it's decimal, but it looks like an integer, but whatever. Extra bottom 7 bits. And this is the hex format. 100101 0x25. Now shift to the right, 7 bits. Still has data, right? Remaining bits still needed encoding. Next iteration. Dun, 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 dun. Step 3 final, extract the lowest 7 bits. Dun, 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 dun. 0 means no more bits left. What's really happening conceptually? Okay, I think we're good with this. So it's going to happen the 7 bits, and using the binary OR operator. I remember reading all of this like a very long time ago, but it's something that I don't use it, so I don't learn them. The bitwise OR operator returns a number of big int whose binary representation has a 1 in each bit position for which the corresponding both operands are 1. Okay, that's good. Yeah, this is a really very good example. A very good example, I think. Is this the one used for flags? I mean for enums. Now this is the thing that I don't remember. In two's complement, right? The most common method represents signed, positive, negative, and zero integers on computers, and more generally fixed point binary values. So with the ones complement and sign magnitude system, two complement uses the most significant bit as the sign to indicate positive or negative numbers. Alright, the left part. Bit numbering is the convention used to identify a bit position in a binary number. In computing, the least significant bit is the position in a binary integer representing the lowest order place of the integer. Similarly, the most significant bit represents the highest order place of the binary integer. I don't want to go and go into a deep dive hole in here, a rabbit hole. So what we're doing basically in this one is, if more are pushed, what I want to understand, and I think this is what ChatGPT is going to help me with. Well, there are more bytes to encode. So is how this line works. Now come back to the top. I want to understand the intuition. Determines more bytes are needed, right? Because what's happening in here, let's try to decompose this slowly in here. I know that here it kind of explains things a little bit. Like for example, given that 7 belong to a number, store them in B. If this is not the last byte, set the continuation bit in the current and push it to the result array. It's the intuition to why be using the bitwise OR operator. To one using the binary OR operator. Okay, so let us read this thing again. Of unsigned LEV128, encodes an integer into one or more bytes where each byte contains 7 bits of real data, 7-bit mask of earlier, extracts the lowest 7 bits, and the continuation flag. It's the highest bit of byte, and that's where we understand. LEV128, since it comes in here, and this is a continuation bit. Example, data continuation bit or encoded byte means another byte follows. Okay, that we understand. File holds the remaining value to encode. More tells if we need another byte, R will connect encoded bytes, while more extracts 7 bits. This isolates the lowest 7 bits of val. Example, 300. Okay, lowest 7 bits. One, 44. Okay, shift away the 7 bits you consume. I understand this. Okay, you shift away. Here we go. Adios. Right. This removes the 7 bits we just encoded. Now we got more equals val. If difference 0, that means that there are no more shifts in here. If more, r dot push. Then where I'm actually lost is what is this continuation bit is doing. Two cases. Add the continuation bit. Canonical LEV, in plain English, this function Can you please break apart the line in which says r.push with the continuation bit? How does that work? The intuition. I love whisper flow. Where exactly how of this line? Here are 7 bits, and there are more bits coming in the next byte. In LEB 128, the 8th bit is the flag. We understand this. So this builds a line with 1 or 7 real bits. Continuation bit. Dun 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 dun. Or why use OR? This is the thing, because OR allows you to add the 8th bit without altering the 7 real bits. Okay. Continuation bit. So that means that R will always hold up to 8 bits. Right? Okay, example, say we're encoding 300, lowest 7 bits. All right. B, binary 0, 1, 1, 1, 1, 1, 1, 0, 28. If more bytes are needed, that byte now means, but wait, when you refer you're encoding 300, what is 300? An integer, a bit, or a number in binary format? What's 28 and 156? Well, we understand they're 32-bit. Different weights. 4, oh, there are 9. Okay, hex 0 to LC. By representation is stored in 32 bits, but at the beginning it's 300 simple integer handler. 7 bit chunks. Okay, so lowest 7 bits, binary of 300. So is this hallucinating? Why is it decimal 44 and not 127? Is the mask, not the result? Oh, but the lowest 7 bits of 300s are not all ones. Right. They're whatever the low part of the number actually is. Oh, shit. Oh, wait a minute. I am understanding now. Oh. Oh, whoa, 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 whoa. I am understanding. Right. Because what we were doing is encoding an integer. That means, right, it's like, okay, I get this. So it's like you're having, like you have this very big box, right? And we're gonna color this. I forgot how to, oh, they've changed a lot. Here we got this box, right? And this box cannot fit in like in the very small boxes. So what we do is that we split. Okay, we want this box and want to fit it inside, let's say, this is going to be a much more better representation box in here. So LEB, at the end of the day, how LEB works, we got here, and we're gonna come LEB. Oh man, wait. Oh wait, let's just zoom this thing in because I don't care about the canvas size. Okay, so we got the LEB 128 encoding. What it's actually doing, so how the LEB works, we got, let's say, this huge number, right? And what we're trying to do, and let's say this number is 335.6, and this is an integer. And we want to actually encode it into a format. It's not, I had it all wrong. So what it's the same as if you're coming in here, you have like these boxes. Put it here, and you have these boxes. And what you want to do is kind of like split it. This is interesting. So what we're doing is splitting this integer. Well, it's more like kind of like here. We're splitting this integer, and we are having this guy fill over here, and this part, since this part is not filled, we want to take it and fill it inside here. Ah, got it. Makes a lot of sense now. That's, I get it. So let me, with that understanding, because what I thought is that we were breaking it up into different chunks. It's like we were trying to reconstruct the number by appending it to the number of bytes. It's, what I'm saying is that you got 356 in here, right? What we wanted to do, I thought that you wanted to create something like 127, and then again 127, easier. So into 127, we got two. So we're gonna have 127 and 127, and then we're gonna add like 0.8 in here, and that's how we would have saved it, right? But of course, if we do this, that means that in here we're gonna come 1, 2, 3, 4, 5, 6, 7 in binary. 1, 2, 3, 4, 5, 6, 7 in binary. And in here, it's, I don't know how do you represent floating point numbers in binary format, but I get it now. You would have like a much bigger array this way. If this would be like integers, you try to break them apart. Got it. So in here, what we do is like we create an array, basically, saying, and little endian order, right? So that's why it's actually saying the little endian first. I'm getting, and now we're getting things. I'm going to explain everything now. The reason why it's little endian, it's because the least part of the integer, kind of like the right side part of the integer, comes first. So the LEB encoding, and this is the intuition I think that we're gonna work out, is that we got a huge ass number in here. We got this number. And what we're trying to do is that we're gonna get its bit representation. I'm gonna say it 366 int 2-bit, the binary conversion, and to sign, I think this is the one, right? Binary number, 9 digits. Is it? Yeah. Okay. Yeah, that's what the, okay, without the precision. and which means it's this one. Ah. So it says it's this one, right? And what we're trying to do is that we extract the first 7 to, let me see it here. 1, 2, 3, 4, 5, 6, 7. And I think this is just a notation. Well, it is little Indian first because you always like how those bits are actually working. So I don't know if big Indian. Okay, I get it. I'm getting it. So what we do is that we extract the 7 parts. I might count to 7, 3, 4, 5, 6, and 7 to this one over here, right? And then we add a flag. Would be the 8th one, telling like, hey, now I want you. I am getting it now. Okay, I am getting it now. I will explain later. The entire concept. Create a concept that holds the continuation bit mask. Initial flag. Dun. Let's start with some boundary numbers. Okay. So there would be something later on that 7 binary, 7n. There will be something in here that we will be able to read back if it has the flag, because what I'm trying to look for right now is whether the bit mask, the first bit mask, actually contains the 128. So how the LEB 128 works from the ground up. I'm going to delete everything. We got, let's say, a number, an integer. Call it 358, 356. And what we're trying to do, since 356 is a much bigger integer than the 127, which we were talking about, it's the least representation to the signed representation. The 128 comes because we have a signed representation to 2 to the 8, which comes from 128 to all the way 128 all the way to 127, because we include the 0, right? So that's why we're working with 128. Now, when it comes to 356, what we want to do is we're not transforming, we're going to encode it in such a way, using bits, since it's the most efficient way to store this number, into different chunks that we're going to be able to read it on 120, on LEB 128. This means on 127 8 chunks. And what's going to happen, that we need a way to learn or to know when there are more numbers. So how this works, we're going to have our binary representation here, 127. I'm going to put it over here. This is a binary representation. Now, what we want to have is like, we want to create some boxes that are 127 in size. Imagine that we have like series of boxes, and these are 127 in size. Well, 128 in size. Tops and tops. But don't think of this as actual numbers, but think of them as binary representations. Just what we're trying to do. No. I'm explaining this incorrectly. I'm actually explaining this incorrectly. No. These boxes have 8 bits. And these boxes have 8 bits. And what we're trying to do is like we slice. The slicing is what is much more the thing that we're talking about. This we're actually slicing this thing. So we're gonna come 3, 4, 5, 6, 7. The first one over here. And what we want to do is that we're going to store this part. We slice this, kind of slicing this. We want to store this part. In here. And then we want to get the remainder part and store it in here. And the reason why we use a little Indian is because we know that this is the first part. This is the least significant part of the bits first. It comes here first, and then the second one comes here. And that's actually the entire explanation of what we're doing. And the reason why we come here and we use the OR binary operator is that if we come here back to this is a bitwise and OR operator, is that we are extracting. Think about this. We are extracting the wow, this is one of the things that you really have to think about it. In here we use it because we are extracting either all of the bits, right? All of the chain of bits, and we can actually tell it that the last one is going to be part of it. So this means that if I come in here, right, this chain of zeros, what I'm gonna say is that after we got the first 7 shifts, 7-bit continuation bit, be 7-bit mask and 7-bit mask. Okay, wait a second. Ta-da. Okay, we extract the 7 bits. Yeah, we make it 1. You know what? Let's do something. Let's do something. And okay, we're gonna come here and let's say let val let more equals true. Const r. And let's say while more const b equals val and 7-bit mask. I'm gonna console.log b. Gonna come here, val equals val, shift 7, more equals val, 0, if more, r.push b, continuation bit, which we have not defined. Const continuation bit equals 0, b1, 1, 2, 3, 4, 5, 6, 7. It's a binary format, and we're gonna say, and it makes it clear that way, or else r.push b. And let me say something, const cont d wait, and I'm going to get this thing in here, maximize this, F12, move the console a little bit in here, and okay, I'm going to say LB 128, say 1. so we need better logging. Say B why are oh right, this is a bug. Okay, and console.log cont. So I want to see how it actually breaks up. Okay, turn val, and I want to see console.log val console.log. It's just a boolean. Lab 128. I'm gonna say 1. B equals 1. Okay, 127. Val equals 0. And right. 26. Why is val 0 again? Oh, because yeah, it just shifts 7, right? So if I say 128 B equals 0, which means it shifted everything, val equals 1, continuation, continue, cont, 128. B equals 1, val equals 0. So if I say 256, 128.2. Really? So 129. Okay, I'm not getting this. It returns to me 130 and 1. Huh. Or is it? Create a constant that holds a continuation bit mask. Initialize a flag called more to know if we should keep the coding. 8 bits. 14 bits. But that's like 2 to the power of 4, right? Power of 4. 14 bits. LAB 128. 2 to the power of 14 minus 1. I did the right implementation. If we should keep the coding. So wait a minute. If I put something like max saving tig, what I want to know is, did I crash the console? I probably crashed the console. I crashed the console. Let me just refresh in here. I probably crashed the tab. I probably crashed the tab. Oof. I crashed it. Seems that Vivaldi is not responding. Alright, let me try with Firefox. Okay, I'm gonna come back, open VS Code, and say delete the console logs, which are probably going to be the culprits. Did it? Oh no, I think I brought the entire browser down. It's like unresponsive. Just quit it. Reopen. And okay, here we got it. We got it back. Okay. Does this work? Yeah, it does work. Okay. We're back here. I'm gonna call F12. I'm gonna paste it again. Without the, and I'm gonna say LB128 number max safe integer invalid array length. Okay, let me just try with something much bigger like this one. So it keeps appending it. Hello, voy para allá. A las 5. Guys, I'll be